Welcome everyone to the last row before the summer break. So we have two speakers today. The first speaker, I'm very happy to introduce Felix Hommelsheim, who is a researcher right now as a postdoc in the group of Nicole Mego at the University of Bremen. He did his PhD at the TU Dortmund University with Christoph Buchheim, and his research is mostly focused on exact or approximation algorithms for combinatorial optimization under uncertainty. He published already papers in math programming and IPCO, and I'm very happy that he's here today. So please, Felix.
Yeah, thank you very much, Janis, for the introduction. So this talk is about recoverable robust optimization with commitment, and it's a joint work with Nicole Mego and Komal Mulok and Britta Pais from Aachen. Okay, so we directly start what we mean by recoverable robust optimization with commitment, and we just start with the motivation and setting, and we start with some example. So consider that you have a car rental company and you own a single car and you want to rent this car to customers. So there are different customers. Each customer has some interval in which the customer wants to rent the car. And also there's some weight which represents the money they are willing to pay for the car during that time slot. And of course, our goal is we want to maximize the revenue. So we want to maximize, we want to select a subset of these customers such that they don't overlap because, we only have one car, so they should not rent a car at the same time. And we want to maximize the revenue. So we want to maximize the weight of these customers that we select. So this then turns out to be an interval scheduling problem as here. So here we are given this set of intervals representing the customers. Each interval has a weight. And then we select some subset of these intervals that do not overlap. So for example, this here would be an optimal solution and would have a weight of 22. Now in our setting, in our robust setting, we have the same setting as before. So also intervals, weights, and so on. But now in our robust setting, one customer might withdraw from contract, which basically means that after we select the solution, one of the customers gets deleted from our solution. However, after this deletion, we again can add one more customer, so one more interval to our solution, if it does not intersect with our previous solution. So if we again consider the same solution as before, then we have these three blue intervals, our solution of weight 22. Now one interval can be deleted. So for example, this interval here, but then we cannot add another of the remaining intervals. For example, this interval here of weight 8, because it would overlap with the interval of weight 2. So then in this case, we cannot add anything and our final solution has a weight of 12. Now, what would be better is to start with this solution where we only add this interval of weight 10 and the other interval of weight 10. Now, if one of these intervals get deleted, for example, this one, then in this final step, we can add again a customer. So we can add, for example, this interval, and we have a second stage solution of weight 18. Okay, so this is now a more robust solution because if some of our customers fail, then later on we can still add one customer and have a good solution here. And this now has a solution of weight 18 in the final step. So to formalize this problem a bit more, we have some combinatorial optimization problem, usually a maximization problem. We call it pi. Before it was simply the interval selection problem. And we have some ground set E, some set of feasible solution F, and some weights on these ground set E. And now the task in our recoverable robust optimization problem with commitment is we want to select a feasible solution. Then in this minimum, one of our elements can be deleted. And it must not be an element of our solution. It can also be any other element or even no element at all. And then in the last maximization problem, we can add again one element to our solution if overall it is feasible. So S minus F plus E should be a feasible solution. And then our goal is to maximize this final weight. So the weight after this deletion and the addition of the element. And usually we call this deletion step the interdiction, and this adding step here the recourse. And what is important here, what is new in our setting, is that we have this commitment. So we cannot delete any of our elements in S that we've added in our previous solution. We cannot remove them except that they were removed by here in this interdiction step. You can also generalize this problem, and there the difference is now that not only one element can be deleted, but say up to k elements. And in this recourse step where we add something, up to L elements can be added. And of course, then the final solution should be again feasible, and we want to maximize the weight of the final solution. So S union R without the set F. And that is the problem we are considering here. And note that these recourse elements that we add, they should not be in our solution and also not be part of F, where F was a set that was deleted in this interdiction step. Okay, so these are like the problems that we consider, and we consider different combinatorial maximization problems pi. So also a different view on this problem is that this inner minimum can be seen as an adversary. So here we can assume that there's some adversary who wants to harm us the most, and this is the interdiction, and we kind of view this as an adversary who wants to harm us very much. Then what's new is that we have this commitment, meaning that the initial first stage solution, we're not allowed to change this afterwards anymore. So we are committed to this solution. And finally, this last step, this recourse, where we can add again these elements to our remaining solution. And this problem pi, this underlying problem, we call it the nominal or underlying problem. And then the robust version of it is called the robust problem in our setting. Okay, so what kind of different underlying problems did we consider? So we have these results here. We can consider the underlying problems: Matroid basis, bipartite matching, bipartite stable set, and interval stable set, which is basically the problem that we've seen in the beginning in the introduction. And we considered the robust versions, and in general, we only considered the 1-1 version, meaning that in the adversary we can only delete one element, and in the recourse, we can only also add one element. Except for the robust Matroid basis problem, there we also considered the KK case, where the adversary can delete K elements, and we can add K elements afterwards. So for this problem, we showed that there is a polynomial time algorithm, and this is also what we see later. For the bipartite matching problem, even this 1-1 case, we show that it is NP hard. And also similarly, the bipartite stable set problem is in this case NP hard. Whereas if we have no weights, so we have an unweighted problem, then this is polynomial time solvable. And this interval stable set problem, this robust one that we've seen in the beginning in the introduction, this turns out to be polynomial time solvable. So in this talk, I will mainly talk about these polynomial time algorithms. So this algorithm here for robust Matroid basis, and the polynomial time algorithm for the robust interval stable set. Okay, so let's start with the robust Matroid basis problem. So our main theorem is the following, namely that a maximum weight basis of a Matroid M is also an optimal first stage solution for our robust problem. So this is very special because in some sense you can just compute the optimal solution to your maximum weight basis problem of a Matroid, and then use this as a solution for the robust problem. And this theorem guarantees that this is always optimal. And since you can compute such a maximum weight basis of a Matroid in polynomial time, then also this problem here is polynomial time solvable. So how does this theorem. How do we get this theorem? So we have some lemma, which we did not find anywhere in the literature, but we assume that this should be somewhere. So we have a basis B, a maximum weight basis of some matrix M, and we have some element F of our basis. Now this lemma says that if F gets deleted from our matroid, then we can add again one element such that this new basis B plus E minus F is max weight basis of the remaining matroid, so of M minus F. Okay, so one element gets deleted from our matroid, and then we can kind of augment our maximum weight basis B with another element such that it's again a maximum weight basis of this remaining matroid M minus F. And we can use this to show that we have a polynomial time algorithm as follows. So we view this interdiction and recourse part not as first the interdiction and then the recourse, but we view it as some kind of sequential part. So first one element gets interdicted, then we can add one element, then one element gets interdicted, and then we can add one element, and so on. So we view this for the spanning tree problem because this is better to visualize than a general matroid. And here a maximum weight basis would be this blue spanning tree here. So this is a maximum weight spanning tree. Now, if any edge gets deleted, for example, this edge of weight 20, then this lemma says that we can add another edge, for example, this here, this orange edge of weight 11, and now this blue spanning tree plus the blue edges plus the orange edges, they form a maximum weight spanning tree in the remaining graph. So where this edge of weight 20 is deleted. And then if another edge gets deleted, for example, this red edge here of weight 22, then again, we can add, for example, this edge here of weight 14, this orange one. And then again, the blue edges plus the orange edges form a maximum weight spanning tree of the remaining graph. So we can do this on and on and on until we reach our K, so the number of elements that are deleted. And now this final spanning tree, it is guaranteed by this lemma that this final spanning tree is a maximum weight spanning tree of the remaining graph. And thereby, this lemma basically implies that our solution is optimal. So after the deletion, interdiction, and the recourse, we have a maximum weight spanning tree of this remaining graph. And this shows our theory. So this is now a very nice property that the optimal solution to the underlying problem is also optimal for the robust problem. And you might ask, okay, are there also any other structures who have this kind of property? And we answer this question with no. So our next theorem states that basically matroids are the only downward closed set system for which an optimal solution to the nominal underlying problem is also always optimal for the robust problem. So if you give me any non-matroid downward closed feasibility set system, then I can give you some rates for these elements such that this property that we had for matroids is not satisfied. So that an optimal solution is not a robust optimal solution. Okay. So this is a result that we have for robust matroid. And now we consider the robust interval scheduling problem. So again, what did we have in this robust interval scheduling problem? So we had some set of intervals, and here it would be not so smart to pick all these intervals here of weight 22, because now if one element gets interdicted, for example, this one here, then we cannot add anything again. But if we, again, as in the example in the beginning, only take those two intervals of weight 10, then if one of our elements gets interdicted, then we can, in the recourse, add again one of these intervals of weight 8, and we have a second stage solution of weight 18, which is optimal in this case. Okay, so our main theorem is for this problem is that there is a polynomial time algorithm for robust interval scheduling. And our main key ingredient is the so-called lambda regret problem. So in the lambda, and what is the regret? So a regret is basically the weight that we lose due to the adversary, meaning that when we pick some solution and the adversary deletes some element, even if we then afterwards can add one element again, we might lose some objective value. And this is called the regret. So in the lambda regret problem, we want to have a regret of at most lambda, meaning that if any element gets deleted and we can then add again one element, we should lose at most an objective value of lambda here. So then this delta fs should be at most lambda, and delta fs is the objective value that we lose if the element f gets deleted from our solution S. This is now here the difference of these two objective values. Okay, and our now you can one can prove that a polynomial time algorithm for this lambda regret problem implies a polynomial time algorithm for our robust interval scheduling problem, because the possible number of different lambdas of different regrets is bounded by n squared, where n is the number of intervals. Because this difference here, there are only polynomial quadratic number of values for this here, and therefore we only have a quadratic number of possible regrets. So if we would then apply this polynomial time algorithm n squared times, we obtain also the optimal solution for our original robust problem. So then what remains is we want to show a polynomial time algorithm for this lambda regret problem. Okay, so first one example for this lambda regret problem. So this solution here has a regret of 3, because if this edge here, this interval here of weight 13 gets deleted, then we can replace this by this interval of weight 10. So we lose an objective value of 3, which is then exactly the regret that we have. And if you, for example, delete the interval of weight 8, then you could add this interval of weight 10, and then afterwards you have even a positive regret for this pair here. Okay, but you can also have a negative regret. So this example here, the optimal solution would pick those 4 intervals. And now the worst case that could happen for us would be if the adversary deletes this interval here. And then in the recourse, we could add this orange interval here. So you might also ask, okay, well, these 2 intervals, they are completely disjoint. Why don't we add this interval even in the first stage? But this is not so clever, because then this kind of so-called backup for this blue interval of weight 90 is destroyed. Because if this interval gets interdicted, we would like to add this interval of weight 100. But if we've already selected this interval of weight 20, we cannot add this interval anymore. So hence this blue solution is optimal. And now maybe one more example where the regret is even more negative, in this case -8. Here the optimal solution would be to pick this, and the adversary would delete this interval here. So not even an interval which is in our solution. And now in the recourse, we would add this orange interval. And again, it would not be optimal to pick any of these 2 in our first stage solution, because then we could not add, if, for example, this interval of weight 90 gets deleted, then we cannot add this interval of weight 100. So this is indeed an optimal solution. And deleting such an interval of weight 19 would increase our objective value by 10. So this would even be even more negative regret. Okay, so now we have seen basically different kinds of so-called backups. So backups are jobs that we add to our solution in case one of our elements from the solution fails. So we have these green backups, which are called private backups. Private backups are intervals that we add to our solution if one element fails and these two intervals intersect. And then these are private because, well, they do intersect. So I can only add this interval of weight 100 if this interval of weight 90 intersects here. And the same is true for this other blue interval of weight 90 and the other green interval of weight 100. Now this orange interval is a so-called universal backup. So we could add this, for example, if one of these blue intervals of weight 5 fails. And this is universal because we can add this interval even to our even into our first stage solution. So this can be a backup for any interval for our solution. And also we have some extra backup, which is this one. And we've seen before, and here, this is the backup basically that we add if this element of weight 20 is deleted. So this is the extra backup. We would add this if our universal backup gets deleted. And now we can transform this into a new problem later on. But first, maybe two observations. So it would not make sense to have two different universal backups because we can only add one element in the recurse. So it doesn't make sense to have two universal backups. And the same is true for the extra backup. So therefore, we know that optimal solution has at most one universal backup and also at most one extra backup. And hence we can simply guess these two beforehand. And there are only in total n square many choices. So this is also polynomial and we can guess those two backups. And then these jobs that have private backups, in a sense, we want to see them as some combined job. And what do we mean by that? This the following. So here we have this interval of weight 90 and the private backup, this interval of weight 100. We want to see this as one combined backup interval where we have some sense this blue colored interval at first, which corresponds to this blue interval here. And then in the remaining part, this part here should correspond to the remaining part of the backup. And also you can see this for this interval here, which also has a private backup. Now for the universal and extra backup, for this interval of weight 20 and interval of weight 8, they are allowed to overlap with these other backups that we have here. So you can see here, this is some kind of a new scheduling problem or interval selection problem where these red parts, they are allowed to overlap. But these blue parts, they are not allowed to overlap. And also these blue parts of the intervals, they are not allowed to overlap with any of the other red parts. So actually we can then, if we have enumerated these, or if we have guessed the universal and extra backup correctly, then we can transform our interval selection, our robust interval selection problem to a so-called interval selection problem with colors. And that's the following problem. Here we are simply given a set of intervals or jobs, which have now two colors as before. So we have two intervals, LJ, RJ and AJ, BJ. And AJ, BJ is the inner interval, which is called colored blue. And the outer interval is colored red. So this is now an instance of our interval scheduling problem with colors. And it is feasible if no blue interval intersects with any red interval or with any other blue interval. So this instance here, this is not a feasible solution because, for example, here, these two blue intervals overlap and also this red interval with this blue interval overlaps. So this is not feasible. But this, for example, is a feasible solution because here only red intervals overlap other red intervals. So with this intuition from before, we can then construct from this solution here, from an instance here of our lambda regret problem, we can construct an instance of interval scaling problem with colors. And for this interval scaling with colors, there is a dynamic program algorithm similar to the standard dynamic program for interval selection that we can use now. And then we can solve our lambda regret version of the robust interval scaling problem by basically reducing it to this interval scaling problem with colors. So the overall algorithm then looks as follows. We simply enumerate over all possible regrets lambda, which are only n square. Then we enumerate over all universal backups u and extra backups b, which are also only n square many. And then for each of these three choices, we basically construct an instance of interval scaling with colors and solve this instance. And here we need these additional properties here, that the weight of this first interval minus the weight of the second interval is at most lambda, which basically means that the regret that we have is at most lambda. So then we solve this for our three choices, and well, among all these choices for lambda, u, and b, we simply output the solution which is the best. And then this, we show that this algorithm indeed outputs an optimal solution to this problem. And therefore, we obtain our result that there's a polynomial time algorithm for robust interval scaling. Okay, so as a summary, so we introduced this new model of recoverable robust optimization with commitment. So here the main difference to previous literature is that we have this commitment. And for this new model, we considered 4 different problems. So the Matroid basis problem, bipartite matching problem, bipartite stable set, and interval stable set. And we developed different hardness and hardness results and exact algorithms. And as an outlook or open problems, so we only considered downward closed feasibility sets. So downward closed means that if a solution X is feasible and X prime is a subset of X, then also X prime is feasible. And we only consider those feasibility sets. If we do not have downward closed feasibility sets, then after the deletion, also feasibility might be an issue. So this would be an interesting other problems to consider. Also, it would be interesting to consider underlying problems that are NP hard and then develop some other algorithms to solve them. And also, what happens if just more than one element fail? So in this work, we mainly considered the case that only one element fails, and it would be interesting to see how the complexity involves if more elements fail. Yeah, thanks for your attention, and if you have questions, I'm happy to answer them.